we have that the electric field given by one point charge is kq over r squared radially outward. If I have a number of point charges, then that simply becomes the summation of individual fields. However, if I have many, many point charges, I could treat that as, hey, the sum of many, many individual fields. But if I broke those up into tiny differential pieces, then this should lead to an electric field equal to the integral of a tremendous number of tiny little differential electric fields, which, since each tiny differential can be treated as a point, I can write as the integral of k dq over r squared radially outward. Now, I can take this value k, or as the book is writing it, 1 over 4 pi epsilon naught. When I get to, I will not make this switch myself until I discuss Gauss's law, just so you can see where this constant comes from. At least I know where that constant comes from. Charles Auguste Coulomb made it up because it made the units work. Now, there are a variety of choices that we have. If I were to take, for example, like a uniform liner charge, and look at some point along an axis bisecting that line of charge, then, the math is actually doable, because if I have a tiny little piece of differential charge dq, then the electric field at some given point will be equal to, if I put this in the x direction, let's see, if I call that theta, then that's theta, and I'll get dq over r squared, which is this distance squared, which is, let's call it y over, I believe that we're going to use a distance r, y over r, so that's y squared plus r squared is equal to the distance squared times the cosine of theta in the x direction plus dq over y squared plus r squared times the sine of the angle in the y direction. And if I need to, I'll adjust that a smidge. But the reason why our life becomes easier if I have this line bisect that line of charge is that for every little piece of differential charge dq right here, there's a matching dq on the other angle that's going to result in a differential electric field in which the y component is going to cancel out. The x component is going to double up, and the y component is going to cancel out. So instead of simply looking at the electric field as the integral from negative L over 2 to L over 2 of k dq, k is a constant, it can come out front. dq, tiny differential charge is what we're integrating over. R changes for each point. So, well, let's say, because I'm already defining r as this distance, let's say s squared for each point, I could say instead that that's 2 times the integral from 0 to L over 2 of the cosine of this angle, which is the adjacent, r over y squared plus r squared to the 1/2, which becomes to the 3/2 when that comes in, times dq, which seems like it's a unhappy, unhelpful pain in the rear because I've got a distance in terms of q. But if I take this charge here and I say, okay, the total charge q is equal to some line charge density as long as I've got a uniform rod of charge, then okay, the total charge is equal to the line charge density times the length. Which means that if I look at a differential piece of these, that a differential piece of charge dq is equal to the line charge density lambda times the differential length dl. So I could instead, which in this case becomes, since I'm integrating on the y-axis, dy, making this equation 2 times k times the integral from z to L over 2 of lambda, which is a constant, so that can come out front, and I break that into q over L, which is also lambda, times, okay, r. R is a constant, so I've got 2k lambda times r times the integral from 0 to L over 2 of dy over y squared plus r squared to the 3/2. Now the first time you've seen that equation, you had to reconstruct this. And there's ways to do this. You've taken Calculus 1. You can go through and find out how to do that equation. Or we could realize, okay, we've done that. Let's look it up in a book of equations or a table of equations, which is perfectly cool. Which gives us that, let me use a different color, the electric field of a rod, as drawn here, will be kq, actually that q is this q, the total charge of the whole piece, divided by r times the square root of r squared plus L over 2 squared in this case, the x direction. Now, there are a couple other useful surfaces to deal with. If I have the electric field of a ring of charge, I'll just write down the magnitude. We'll keep track of the sign with the direction. If I've got a ring of charge, then the electric field of that ring on the z-axis, if the ring is in the xy plane centered on the z, that gives us k z q over z squared plus r squared, the radius of the ring, to the 3/2 power. If I have a disk, then basically I'm taking that ring and I'm taking a whole bunch of rings, and I'm integrating from r is equal to 0 out to r is equal to the edge. And I find that value is equal to the surface charge density, the total charge over the total area, divided by 2 times epsilon naught. From that equation, I can also write that as 2 pi times k epsilon naught times 1 minus z over the square root of z squared plus r squared. Now, if I take this result and I expand it out to a plane of charge, then that's basically saying, okay, well, what happens if r goes to infinity? The electric field of that plane will be equal to, whoops, not n, this is an eta, that surface charge density, divided by epsilon naught, which I can write in terms of k by writing 4 pi k times eta. Now, I did this one in a little bit of detail, and all the rest of these are done in the book. This learning objective 26.3 requires you to be able to use any one of these and recognize these. On your formula sheets, I'm not going to necessarily say, this is for the rod, this is for the ring, this is for the disc, and this is for the plane. Your practice homework should make you familiar enough with which is which to be able to answer that yourself.